Yeah, here is a prime topic like research contributions of DGC in CFRP technology for the nation. And this presentation includes a small introduction on the presentation and the drive for the research and the technologies that we have developed, and which also includes the in the basic introduction. I would like to say that this FRP technology is being in practice from last few, I would say, a decade. Almost every kind of structures can be done by FRP methods nowadays, and DGC has got a a breakthrough from Western where we have retrofitted a PSC eye girders, and now the immense research and the immense practice in this technology in is really a way front to appreciate. What is the drive for this research? So that the complete strength of the FRP is not being used in retrofitting of any of the structures, I would say. The tensile property of attracted the researchers and the applicators in this particular field. So in this direction, we always believe that there is a so the technologies that we have developed is pre-stressing of laminates by pre-stress machine and carbon anchor application, triple laminate stressing technology, and band stressing methods and application of glue laminates. So I like to discuss one by one. So definitely the pre-stressing of advantages like this makes the system active, and comparatively higher strength of CFRP is used since we use a strain in the laminate, and it creates some reversal moment in the structural member, which counteracts the effects of the initial loadings. Is more evenly distributed, and hence it avoids the bond failure to some extent. So these are the components of pre-stressing machine. This is cylinder body. So this is the anchor plates which we finally place at the ends, and this is the machine setup. So where the pre-stressing technology is being used, and I would like to show this video. Yeah. So machine has got two ends, like one is fixed and the other one is movable. The cylinder body is placed at the movable end, and which accommodates the jack. While loading, this movable part will move backside, and it induces a design strain in the CFRP laminate. And there is another technology which we have developed, semi-stressing of laminates. So stressing method, but applicable where there is a not requirement of reversal moments. We could make the system active without so again, this is fast in application, and it is easy to handle as well. One fixed end and the other one is mobile end. In this technology, we induce about 400 to 500 kgs of stress in the laminate, and we make that active. So this is completely a manually operable machine. using this technology in a strengthening of slab and flat slabs and the PT slab. Let's go into one more technology called band stressing method. We generally know the columns are confined by CFRP sheet. Gives us the provision to stress the confinement. Stress the bands that are being used for the confinement. Increases the confinement property in the column. See. So there are other advantages as well. If the crack section we are treating, there will be reduced deflections and reduced stresses. And definitely it again participates in some of the photographs where band stressing being used, and this is one of the video how the stressing of the bands, CFRP bands are is applied to the overlay first, and then the CFRP bands are placed and they are stretched. Yeah. Apart from this, we have one more machine where the three laminates can be stressed in one shot, and this is again another. And this is applied where there is a limitation of girder width and time of operation, generally in railway bridges, where we get limited block time and the strengthening work. So, and it is very fast in operation since we are doing 3 laminates stressing at a time. Very easy to handle. So these are the setups showing the triple stressing of laminates. Application. This we have been practicing from almost a decade, I would say, where the groove laminates are inserted inside the column, and these are generally where the columns are being subjected to tensile forces. This is one of the project where bowstring bridge having a using these NSM FRPs, groove laminates. These laminates are anchored at their ends for better anchorage system. Very much valued where there is a space constraints. And again, this is one of system that we have introduced, carbon fiber anchors, to integrate the core concrete with a FRP overlay. So basically, we drill a hole, we make a provision, we apply this CFRP laminates, we insert these anchors inside the concrete, and then we spread the threads across in a set. This actually integrates the FRP system to the core concrete, and also like this helps in debonding strains. The design, when we consider a debonding strain, this gives little allowance in considering high value of debonding strain. So, and also when the aspect ratios are high, while and has been very effective as well. So these are some of the codal references which effectively speaks about the things and retrofitting of flexural members. So under conclusion, I would like to say, since as very little like we are using very less property of the, a very small property of this this trade, not to the higher extent. So there's a requirement of development of technologies in this domain, and DGC has always been quality and optimized services for its clients with its extensive research in this particular domain. And lastly, I would also like to say we have been the technologies that we have developed is being replicated in ASTR guidelines as well, so which we are really proud of.
How responsible are design and construction, mind you, not only construction but also design practices for large number of present day failures? There can be many reasons. For example, lack of understanding of the codes of practice by the designers. This has been found to be a reason. Underestimating of the construction loadings, because their loadings are supposed to be taken on the bridge design while designing the bridge, and nothing should exceed. If it does, it has to be accounted for. Like, for example, your bridge may be designed for the permanent loadings, service stage loadings. But if there is any construction loading, which may be a launching girder weight or something, and if it makes the structure more severe at certain location, then the structure must be designed for it, even though it happens only once. Improper construction sequence. The sequence of loading or sequence of construction has to match the design, which again I will show you some examples where how sequence can affect the designs. Inadequate quality control, we always talk about it. And improper control of documents, which means that the owner or the client has issued drawings which are revision R6, but the construction is happening with revision R5 or R4. And then something is bound to go wrong. Why? Because the procedure to mark the old drawings superseded, and marking every print superseded was not followed. In fact, if you go into ISO documentation, there's a procedure that says that you have to mark, first of all, when you issue the copies, drawings, etc., you have to count the numbers and document it somewhere that so many prints have been issued. Then once it is updated, then the older ones, each of them with a number, given number, should be marked obsolete. Talking of the first topic, that is loadings. New loadings have come in IRC 6, which is in 2017, where there is a special vehicle load that you see on the left side. There is a vehicle congestion factor. We can debate as to why and how, but these loadings may not be known to designers at times if they are not aware of the latest codes. Or if we see IRC SP 65, which is for the segmental bridges, it was first prepared in 2005 and now modified to limit state method in 2018. This may or may not be known, and I have recently seen an example where people didn't follow this code at all for a segmental bridge. Seismic design of bridges. There's a new guideline altogether which replaces the provisions of IRC 6, that is IRC SP 114, that has to be followed compulsorily for the new bridges. So this people may or may not be aware. That's my point. Okay, let's look at some examples. What can go wrong? Because I have to be short and try and finish by 6 o'clock my time. Okay, so here if you see this diaphragm which you have, the pier diaphragm at the end of a box girder, it is so very important from the design point of view because it may look very simple, very deep beam kind of a thing, but it carries the entire span on it, the entire weight of 500,000, 2,000 tons on it. So where it supports the bearing is very important. Where it's rather not supports, gets supported on the bearing. Where it gets supported during the construction stages on a temporary stools, or where it gets supported during replacement of bearings on a temporary jack. Every condition affects the design of the diaphragm. And if there's a cutout like this for excess, it makes it even worse. So I will show you an example where when you have a diaphragm that looks something like this here, let me just put it to presenter pointer option and go to laser pointer. Okay. So this kind of a opening that we have, And I will show you some pictures as to how it has created so many problems in many spans. Those openings that we saw in the diaphragm, on all the four faces of the opening, the lower one is a plan, of course. So you see these longitudinal cracks. There are longitudinal cracks again. There are longitudinal cracks almost everywhere on all the four sides of the opening in many, many spans. Reasons may be many, but such things are happening. Okay, let's look at what we talked about, the construction sequence. Uh, this is of course our project that we did 45-meter span spliced girder, wherein each of these girder pieces, which are pre-tensioned, are 9 meter long. They are placed on the supporting formwork, and after that, after they are placed, these wet joints are concreted, and thereafter we have to see the deck slab and the pre-stressing. Now, what can go wrong? Let us see. One possibility can be that you pre-stress the girder alone first after wet joint is concreted and the concrete gains strength. In which case, the pre-stressing would be imparting its stresses or its forces only onto the girder section, and the slab comes later. The other condition can be that you first cast all these wet joints and the deck slab. Until that time, it rests on the same support at the bottom. And now you pre-stress, wherein the pre-stress is applied to the composite section, including the slab. The behavior is absolutely different. Design has to match what site will do, and site has to match what design has presumed. Stability has become a very difficult problem and very frequent problem in our country over the last several years, including today, is that when you place a girder, precast, it could be pre-tension, post-tension, doesn't matter. It has a span, let's say anywhere around 20 to 50 meters. It has a height anywhere around 1.5 to 3 meters. This girder by itself is fairly unstable, but not theoretically unstable. If it's placed on the proper support here, here, it is not theoretically unstable, but still stability arrangements have to be provided, because there have been umpteen number of cases where number of girders have fallen down. And even 3 days ago, some cases taken place like that. So what we do is that when we place the first girder, we provide this kind of bracings to make sure that the girder is stable in itself. Only when these bracings are connected, you remove the crane support. Then you bring in the second girder, connect it to the previous girder with at least some supports horizontally, so that this girder will form like a truss and triangular truss, and this truss will not allow this girder to fall. Then you do third one, fourth one, whatever. And the last one, again, as you notice, is once again braced. So now over the next 7 days, 10 days, 2 months, 5 months, 6 months, whatever time it takes for the top deck slab to come, these two sets of bracings along with the horizontal rebars connected is stabilizing the entire arrangement of 5 girders. One can also see another example here. This is from a different project in Delhi, that girders are stabilized in a fantastic manner. Each girder independently is connected to the pier with the fasteners below, or with the anchor bolts, before the next girder is placed, and of course the other girders are placed. Now I have seen an example where these things were provided, but these bracings were missing. Pier cap was covering the entire set of, this is an accident that took place about, I think, 2 years ago. I had visited the site. Pier cap covered all the girders, and there were 1, 2, 3, 4, 5, 5 girders, yeah, parallelly. The central girder was supposed to have a pot bearing which would be transversely fixed, and they were placed directly on the bearings, pot bearings, therefore no question of temporary stool or anything. And these two girders, the outer two on left and outer two on the right, would have transversely free bearing, which means middle girder would have, or central girder would have, transversely restrained bearing. The outer two on either side will have transversely free bearings. Now what these people did, unfortunately, They connected girder number 1 and 2. They connected girder number 4 and 5, but they did not connect girder number 3, which is the one having transverse stability with the fixed bearing or restrained bearing transversely. And this was lying for almost 3-4 months like this. And there were heavy dust storms and all kinds of storms and everything. Slowly over the months, it so happened that both these girders slid and they fell down. They slid and they fell down. And of course, casualties and all that is a part of it. So when we explained that why it has happened, they just repented. Oh, we never thought that this could be so simple an issue which we didn't take care of it. Imagine if they connected all the 5, then chances of this failure would have been more or less avoided. All right, so now we go to another example where a flyover has fallen down uh, for a very different reason as it is surfacing today, is that the temporary supports are not permanent bearings. These are temporary supports below the girders, but each of the supports, which is supposed to be at least a metallic stool or a wooden single wedge, is really speaking comprising of several numbers of wooden pieces to form it, and wooden pieces can tilt, and when they tilt, the girder tilts, and when the girder tilts, it falls. And why it falls is that if, let us say, girder has just tilted and come onto the pier cap, girder has a span, in this case it is about 40 over meters. The girder's major axis goes horizontal, whereas minor axis becomes acting in the vertical direction. So the entire weight of 30-40 meter span is coming in the vertical direction where it doesn't have the moment of inertia, the Z or the lever arm. And therefore the girder, moment it tilts 90 degree, it has to crack. And once it cracks, it has to really fail and fall. And which is somewhat like that has happened here. There's one more picture. Because these are all consequences that there's a truck below, or there's a car below, or there are deaths and there are accidents, all of those things. But reason was some that you know. So today our idea is to know that what all can happen, why it can happen, and there are various possibilities. It's sometimes very difficult to even know what the reasons are. Another flyover, which is a segmental flyover, just that the bottom side of concrete of this segment is poor. Not much of a stress. You only know, you see this 15 MPa. Even if the concrete is M40, it can take 20, 25, 30, 35 MPa also. Although with the factors of safety, it will be much lesser, but certainly 15 MPa is not a problem. 0.48 FCK or 40 MPa is 18 FCK, 18 MPa. But because the concrete at the bottom is poor, and when you put all the pre-stressing at the bottom, majorly at the bottom in the middle of the span, it gets compressed, it gets crushed, and it gets lifted up. Now you have no other choice. You have to remove this span. There's nothing that you can do. So this is a picture which shows very clearly that the top concrete is somewhat better, bottom concrete is more poorer. And this happens because majorly, of course, one of the common reasons that at the bottom you have several, pre-stressing ducts. And these ducts may be as much as 100 to 150 millimeters in size. The concrete sometimes may not reach below these ducts. You may see the concrete at the surface good enough, clear enough, but inside the ducts, or in between the ducts, the concrete may not be properly reaching. There may be voids unless you carry out a proper UPV, that is ultrasonic pulse velocity test. You will not know that there are honeycombs inside. Outside is all intact. You don't see any problems. Only when you stress, you get this kind of a problem, and this has happened. And then of course you have to support first to make it all stable. It should not just fall on somebody's head. So you put all these supports. These are the pictures of those supports. Now you start breaking everything. There's a process. And now you have to take out these segments. So whatever you did for launching the segments or the launching girder, now you back move everything, undo everything, take the launching girder back, connect all the segments back again, and then saw cut the segments and start lowering them to remove. Another case, very similar. The bottom was very weak. Bottom being very weak, what happened? It was extremely weak. So it may have slightly hogged up, but since the whole thing was so weak, finally it fell down. So this became a worst case that the span actually came down to the ground. There's another example that's in Mexico. They say it's the worst disaster in the previous 50 years of a metro project, girder slab, and it has fallen so badly like this. They're also investigating the errors, whether they were design or construction, or they think it is both. So these are some more pictures, and then you do some temporary arrangements like this. All those things are a part of the work. One more thing that we have seen happening at places is that epoxy application. Between the two segments, there is an epoxy. Looks very neat. But do you see epoxy? I don't see epoxy. It should not be as neat. As per the codal stipulation, you're supposed to apply 1 mm epoxy on both the surface. And after you apply the temporary pre-stress, it should become nearly half of it after application of the pre-stress. How will it become half? Some will go on the other surface. Some excess epoxy will come on this surface. It looks something like this. If you see, it's looking dirtier. That's what we want it to look like. And thereafter, you scrape it out and remove the excess epoxy so that it looks neater. But it should not look neat right in the beginning when you stress temporary pre-stressing at the left side. Okay, come to the match casting or casting of segments. Segments are cast by match casting technique, wherein you cast one segment, cast the next segment against it. And there's a complete matching of the surfaces. You may cast 1, 2, 3 like that, or 15, 14, 13 like that, or you may do 1, 3, 5, 7, and then in between by match casting. But what is important is whatever match casting you do, like this one is 1, 3, 5 type of a condition, that first you put the bulkhead here, we put a bulkhead here and cast these segments. We put bulkhead here and we put bulkhead there and cast these segments. And in between the two, we cast a segment directly against the surface with a separator, bond breaker. Each segment must be given a unique identification number. Unique means for which span it is, which is a segment left side of it, which is a segment right side of it. You cannot use a segment of one span into another span because it has to match with the same segment against which it was cast. That is fineness. And the other important thing, of course, in the design to take care of the during construction condition is where the segment has to be lifted from. At times, at this location, you get some bending moments which are different from what you get in the service condition, and you need a special design for this. Many times you must have noticed that segments are lifted from cantilever wings or cantilever flange slab. When that happens, you have a tension at the bottom during lifting, and for that tension you have to provide the reinforcement at the bottom of the cantilever slab, which otherwise is not required in service condition. So the designer has to know that he has to cater to the construction conditions in his design fully well. Another case we have come across is, say in this case, it's a 5-span continuous structure. At this place, they have decided to have 2 rows of fixed bearings. 5-span means this is free, longitudinally free, free here, and free here. So P5, 6, 7, 9, and 10 are free, but the P8 is a restrained case, longitudinally restrained bearings. But what somebody has thought of is to provide 2 rows of fixed bearings, or 2 rows of longitudinally restrained bearings. That is, you see here, longitudinally restrained, transversely free, both are longitudinally restrained, transversely free. Or if you see the enlarged view, they call it FX and FX, that means fix and fix longitudinally. Now look at the repercussions. There's a distance of 2 meters from here to here. That is, from one fixed bearing to next fixed bearing is 2 meters. The 2 meter long structure between the two lines of fixed bearings will have to breathe on account of temperature, creep, shrinkage, etc. Once it breathes, the structure has to expand or contract, come what may. Finally, what will happen? That the bearings will tend to fail. And we don't want this to happen. Therefore, and I can understand why somebody would have done this. They want the longitudinal force due to earthquake and braking to be shared by two sets of bearings and not one. But the repercussions are that during the movements, the bearings will fail because they cannot move. They are both longitudinally fixed and the structure has to breathe. So either bearings will fail or the structure will show a lot of cracks. The other causes that again are coming from experience, by the way. Bearings have been placed upside down in certain cases. Since they are doing a large number of spans, long viaducts, they forgot to take care that certain bearings have gone upside down. If you have a pot bearing, if it's supposed to have bottom plate at bottom is going to top and the vice versa. Sometimes when I've seen that, especially in the guided bearings, they've forgotten which direction the bearing has to be placed in terms of plan. And they have rotated 90 degrees in plan. The other problem one has seen at times is that the structure temporarily, before it is made continuous and the fixed bearing starts acting for the entire structure, is not temporarily locked against longitudinal movements. We usually design a temporary lock for 5% of the vertical load in such a way that in case an earthquake takes place or something else happens, the structure is not free. It is at that time connected to the bearing, to the substructure. The lock will be released only after the structure is fully connected to the fixed bearing, at least at one place. Another type of failure, again, is coming from experience only, and Mr. Jatkar is well aware, he's with us, and I think Mr. Hegde as well, and of course many others, is that many times the segmental structures are constructed using ground supported staging. No issue, it will be slow, but no other problem. But ground is being used by public, remember. You have to control that public that they don't spoil your supports. Otherwise, this can happen. Now, the reasons. The place I'm talking about is the one where there's a slope of 11 meters over a short distance. Right side on the picture is 11 meters higher than the left side. And all the supports that you saw just now are there at the lower level. All that is fine. But one work of the laying of the pipeline for the water of 1 meter diameter was going on. And those pipelines were laid from upper level every day proceeding certain meters towards the down level. And those people, when they go back in the evening, they're supposed to close the end of the pipe so that the water from the higher level does not travel in the pipe and go below, which is exactly what happened. They didn't close it. There was a heavy downpour. The water came underneath these temporary trestle foundations, undermined it, trestles tilted, the whole structure fell. Another kind of a problem. This is a simple foot over bridge. Okay, I should finish in 5 minutes. I hope I can. Foot over bridge, which there are outriggers which are connected to vertical suspenders in stainless steel. An accident has taken place. This is, I think, well known to many people. What is important here, apart from other things, is that this connection with the vertical suspenders to the metallic structure, this must be made properly, because in this nut or bolt that is there, the bolt has only half thread extra. In case you go wrong in fully tightening the bolt into the nut, just by half thread if you're away, then the whole thing can open out like this. All the forks are open, the structure comes down. The other thing one has seen while designing the foot over bridges, most people don't seem to take care of the fact that it has to be designed for vehicular collision, which means if a vehicle is running on the road, it collides the foundation and this part for a height of 1.5 plus another 1.5, 3 meters should be safe against that vehicle collision force, which is in the range of 50 tons and 25 tons and all that. And of course, when we designed this structure about 10, 12 years ago, this reduced force provision was not there. It was 150 tons. So we designed this literally for that force, and the foundation became as big. Has anybody, I mean, ever seen, I'm sure, in some of the structure, but not very many, we have such a huge foundation for these two spans, which are 35 meters each. Unless the foundation is 4.5 meters away from the curb, you're supposed to design it for that force. And I think most people tend to forget that. And they end up providing a simple pipe here of whatever half a meter diameter or some 600 mm, and they live with it. They forget that an accident can take place. Look at another type of condition, which of course is there very well in IRCSP 66, but many people may not be aware. In a continuous bridge, when you have a fixed bearing, not fixed really, it's a longitudinally free, transversely fixed. So it's a guided bearing. What should be the direction of placement of the bearing? The movement of the structure for which you are trying to cater to the movement actually takes place. Like if you are putting a bearing here, okay, this fourth one from the left is the fixed bearing case, or third one from the right. And if you talk of any typical pier, let's say if you talk of the first pier on the left, the guided bearing here will be aligned with this straight line, not radially, not circumferentially. It will be aligned with this straight line that we must remember. And this has been codified about 15, 16 years ago. Mr. Alok Bhaumik, I don't know if he is there, he prepared this code. All right, remediation. I'll go very fast, finish it in 3 minutes. We get cracks like this. If there are narrower cracks, we seal them with epoxy, or we seal them with polyurethane. If they are thicker cracks, wider than about 0.6, 0.7 millimeters, we can even grout them with cement. And if they're even wider cracks, we can do anything. But if they're less than 0.2 millimeters, then just make a V groove and fill epoxy putty and nothing else, because no material under pressure also will go inside. The strengthening of a structure after the failure or percepted failure can be metallic, non-metallic, external reinforcement, or external pre-stressing. A famous example of Thana Creek Bridge, they have used, apart from other repairs and everything, they've used external pre-stressing to strengthen the bridge, to retrofit it basically, which one can see the pre-stressing outside, and I think many people would have seen it. In the case of Sharavati Bridge in Karnataka, this was a condition of the rebars. This was a condition of pre-stressing strands. It was so bad that even an endoscopic camera could go inside the ducts and take pictures. So they had to carry out similar things. That is, first the crack sealing, then some patch-up mortars, and thereafter, this anti-corrosive stuff and external pre-stressing. This part, I think, has already been discussed by Mr. Chandar from DGC, that this kind of external non-metallic reinforcements, which can be pre-stressed or non-pre-stressed, can be provided in terms of either a wrap type of a thing, sheet, or in terms of a plate. And all these things are very well covered, that you're permitted to use these materials in IRCSP 40 and also IRCSP 80. This is a pre-stressing jack that he showed, very similar. So these are those codes, SP 40, SP 80, they do cover about these, advanced composite materials, which is basically carbon fiber polymer or glass fiber polymer. In one case, we had this kind of cracks in the diaphragm over the opening, and this cracks here also. So we decided to go for two schemes. One scheme was to provide external pre-stressing in metal on either side of the diaphragm. In the other case, we decided to do FRP, fiber reinforced polymer. And finally, they executed this FRP because it's thinner, lighter, easy to apply, but it's more expensive. But once you do any kind of a repair or any kind of a remediation, it's very good to load test the structure to see that at least it can take the vertical loads well as per the IRC.